Today we are going to discuss solving rational equations graphically. And by rational equations, I'm talking about functions that are in the form of 1 over x, which graphically looks like the picture you see over here on the right. We have an asymptote that is vertical and horizontal, both at x and y equals 0. And this is just an image that you should be familiar with a little bit by now if you are going to be watching the content of this video, because I am assuming you understand concepts like asymptotes, common denominators, and things along those lines. So let's just go ahead and jump into what one of these equations and situations would look like. Consider the equation 1 over x minus 5 plus x over x minus 3 equals 2 over x squared minus 8x plus 15. Let's talk about a couple review concepts really quickly just to make sure we're prepared for the content that's going to appear in this video. For instance, you should be able to notice that the left half of this equation, if you were to make it its own equation with a y equals in front of it, then it would therefore have a domain of x and x not being equal to 3 nor x being equal to 5. And that should be a obvious thing because we have a denominator situation where, since it says x minus 5, you would not be allowed to plug 5 into that denominator because that would mean 0 would become the result, and you are not allowed to have a 0 in the denominator. Hopefully that concept is something that you are familiar with, because I am assuming you know it if you are watching this video. And what you are also observing right here with the domain is the interval notation way of representing it. Right below where it says x is not equal to 3 and not equal to 5, that's just another way of representing the domain, both of which are valid. So the main point, if you were to take the first half of this equation and make it its own y equals function, then it would have a domain that excludes positive 3 and positive 5. Taking a look at the other half of this function, it does have a denominator that can be factored, the x squared minus 8x plus 15. And if you were to factor it, which is again something that I'm assuming you are already familiar with if you are watching this video, then you would get a denominator of x minus 3 times x minus 5, which I will make a point of saying is a sheer coincidence that it is the same pairing of denominators from the left half of the equation. Everything that I'm about to show you would be the same procedure if instead of a 5 and a 3, you had a 1 and a 2. Everything would be operating the exact same way. It's just a coincidence that both answers regarding the domain are the same two numbers of 3 and 5. Just take note of the fact that after factoring that denominator, we now have x minus 3 and x minus 5, so that means the domain would exclude 3 and 5. For the same reason before, that the denominator would become 0. Now, let's go ahead and take this equation, now that we're sure that we know what domain means and we're going to have some asymptotes appearing. Let's see what this looks like after we graph it on any graphing tool like Desmos, and here's what it would be. Now, take note of the color coordination that has been used here and the fact that now we can see there is a blue and a red graph. We have a point of intersection. That point of intersection is going to be your solution, and it is right over here on the left. It is where you have the -1 value for x, and that is going to be a solution to this equation. And hopefully from Algebra 1, you have seen moments where a graph might have two lines that are crossing, and where they cross, that intersection point is going to be your solution. This is the same idea, we just have rational functions instead. So something else to observe, the values of 3 and 5 are both being represented as asymptotes. Hopefully you are going to anticipate seeing vertical asymptotes at the locations of 3 and 5, and it should be obvious, but just in case, asymptotes can absolutely not be solutions because they represent invisible barriers that the function will never touch, it will never cross, and therefore will never be a solution to the equation. So based on this graph, without even solving this equation, we haven't even talked about how to solve this without a graph yet. Just seeing where you have a point of intersection, you're going to know the x value that is the solution to your overall equation. And if, for example, you were to perhaps solve this equation without seeing a graph, you might get an answer perhaps like the number 5. And you might think that that's a correct answer, but visually you can see that 5 would be an asymptote on this graph and not an actual solution. So that brings us to the next skill we're going to look at. What if you did not have a graph anymore and you just had to solve this algebraically? Now this would be a good moment to pause the video and set up this equation and maybe get a couple colors and highlighters prepared, because the procedure I'm going to show you is something you are going to be doing a little bit more of in some videos to come when we explore how to do these equations without a graph entirely. So take a moment, pause the video, set this equation up, and hit resume when you're ready. Okay, here we go. So before we get into the solving idea, I just want to take a moment to relate this equation to something that is hopefully relatable from the past. Finding a common denominator. That's what we're going to do here in order to solve this equation. Right now, our denominators involve binomials and a trinomial, and we need to find a common denominator. Here is a simplified version of the situation you're in. Notice how I removed the x's from the denominators and only left the numbers of 5, 3, and 15. Now, this equation is absolutely something you might have seen in an Algebra 1 classroom, and here is the strategy that you could use, that you're going to need to use today in order to solve it. You're going to want to multiply both sides of this equation by the least common multiple of the factors of 15. The factors of 15 being the numbers 5 and 3, the other two numbers that you see on the other side of the equation. When we multiply both sides by 15, that's just like taking the binomial from the original equation and factoring it into x minus 3 times x minus 5. We're going to multiply by 15 in this simplified example, and then you'll see in a moment where we're going to multiply up here, or even perhaps pause the video right now and think, what are you going to multiply the original equation by, now that you can kind of see the relatable concept, but nevertheless, let's just keep going. Once you multiply both sides of this equation, everything on both sides of the equation by 15, here's what's going to happen. Your 15s are going to cancel out on the right-hand side with the 5 and the 3 in the denominator. The 3 in the middle term's denominator will divide into the 15 and leave you with a 5 that you can see right here. And then lastly, the 15 at the beginning is going to be divided by the 5 and leave you with a 3. Now, when you bring all the work down, you're going to have 3 times 1 as 3, 5 times 1x is 5x, and then the 15's canceled out entirely, so just the number 2 is going to drop down. And this function, this equation, is something that can be solved. You would just subtract 3 from both sides and divide by 5 and you'd be done. Now, we're going to take this idea and now apply it to the original equation that we now have to solve. And whether or not this related common denominator situation made sense, here is the work you're going to want to take down in order to proceed with, the way this is supposed to be done. So once again, we're going to start by factoring that denominator and rewriting the problem once that denominator is factored, and we're going to multiply both sides by the least common multiple of x minus 5 and x minus 3. And you can see exactly what that is now. Perhaps you guessed it before. You are going to multiply both sides by the factored binomials, the factored trinomial x minus 3 times x minus 5. And you're going to look just like this. You're going to give a multiplication moment to all 3 of those parts of the rational equation, and here is what it's going to look like when you start canceling things out. If you see the same thing in the numerator and denominator, which, by the way, all 3 of these would technically be numerators of fractions when they're multiplying, so that's going to play into how things will start to cancel out, but let's just go ahead and continue with that right here. We have an x minus 5 in the denominator, and that will cancel with that x minus 5, and x minus 3 will cancel with that x minus 3, and then the entire denominator underneath the 2 is going to cancel out entirely, leaving you with the following. 1 times x minus 3, and then x times x minus 5, and then the 2 is just going to drop down. Now, this is a critical part in the problem where the main concept has now been explained. I'll quickly reflash the original situation here just so you can see what's happening. We factor the denominator. We then assess what are the common factors that we will need to multiply on both sides. And since the only denominators we see are x minus 5 and x minus 3, and on the other side it's the same pairing of denominators, then we are going to do what it says here in blue. Multiply both sides by x minus 3 times x minus 5. And when you do that, you are going to be allowed to cancel out your denominators that are matching. So the x minus 5s, the x minus 3s, and then both of the binomials in the denominator where there is the 2. So with all of that work now done, once again, you are going to have the following expression brought down, which is something that you can now solve by using, a little bit of the distributive property and then factoring skills. So after doing that, you would distribute the x in the middle equation. That is the only distributive property moment you can have. And now we have to work our way towards factoring. We have some like terms that we can combine, and we need to set the entire function equal to 0. So you can see the x and the negative 5x combined to make negative 4x, and then the 2 right over here on the right, we would subtract 2 in order to set things equal to 0. And then through factoring skills that I'm assuming you are already somewhat familiar with, and then using the zero product property, you would be getting the two solutions of positive 5 and negative 1. Now remember, all of this came from a graph that we were originally starting with. And if you never had that picture and you just solved this equation and you would get 5 and negative 1, you might think that you're done, when in reality on the graph, negative 1 was a valid solution because we have a point of intersection. However, positive 5 was an asymptote. If you saw this picture, but then right over here, you had your two solutions of 5 and negative 1 already established, then you would know right now that positive 5 is not a valid solution. It's an extraneous solution. Perhaps, though, you're not going to get the graph, which is a skill that's going to be coming up in a later video. This is what you would do in that situation. Verifying these solutions algebraically means, just take a look at your denominators. If we were to plug in positive 5 wherever we see an x, you would immediately get a 1 over 0 in that first part of the equation. And since you can't have a 0 in the denominator, 5 could never be a solution to this equation, and you would therefore know it's extraneous. Likewise, if you were to plug in negative 1, all of the denominators would not become 0. I don't need to take the time to finish solving this. You already know that you're not going to get a denominator of 0, so you know that negative 1 is a valid solution. So, therefore, in conclusion, once you have your two solutions, or however many solutions you get, visually, your points of intersection are going to be the solutions, the asymptotes are not. But if you don't really have a picture, then you would need to plug your values back into the original equation so that you know what is valid and what is extraneous. On that note, here is a practice problem that you can now try. Something to take notice in this practice problem: you are seeing the visual and then you're seeing the equation down here in the bottom corner. I will let you know right now, you can tell what both solutions are. I have written a black X over them. You can see they are 0 and 0.5. Now, knowing that information is going to allow you to practice solving this function with a little more confidence, because now you know the two solutions that you're supposed to get. So right now, I want you to pause the video, take this equation you see down here at the bottom, and practice the skill of multiplying a common denominator on both sides in order to get the two solutions that you see here. All right, and on the next slide, I'm just going to let things play through so that you can see how all of the work comes together. Thank you for watching the video. Please leave a comment if you have any questions, and I will see you next time.